Okay, good. Thank you for coming. I'd like to thank also the organizers for the invitation to spend time here in Paris, and it's of course lovely to be here in Paris, and any time, but this time of year particularly. It's an honor to start off this workshop. As you'll see, what I'm going to tell you about is not so much analytical methods in cosmology, but it'll be actually not so much about cosmology at all, but it's when you organize these things, I think people can't predict where these talks are going to go. So the title looks different than the one that's in the list, but it's really the same idea. So because we're in Paris, I wanted to start off with a Paris reference in the front page, and of course failed. It was I'm immersing myself in the history of what's going on here. I thought I could make a connection between Newton and Louis XIV. Through the quote, La loi c'est moi, but when I actually checked what was being meant by that quote, it turns out that quote is from Sylvester Stallone in Judge Dredd, and of course Louis XIV said, L'état c'est moi. So the only thing I have here that's authentically French is the croissant, which is forbidden, and so what can I say? So I'm going to be describing work done by, together with Rich Holman, Greg Kaplanak, Gian Massimo Tassinato, and Matt Williams, in those references there. And mostly I'm going to focus on the last one, which is the least cosmological of them. So before starting the talk, let me give you the sales pitch so you kind of see where I'm going to go before I get there. And basically, part of what I want to do is undermine the point of view of gravitational exceptionalism, which the cartoon of which is that gravitational physics has nothing to learn from other areas of physics. That really, it's different. It's strongly interacting in a way which is unlike other kinds of strong interactions. And I have a picture of Einstein here, which is really completely not fair because I don't think he was really advocating it, but I needed somebody who was definitely associated with gravity, and I didn't want to slander anybody who's alive. And so the alternative point of view to that would be what you might call gravitational banality. And this, I've got a picture of Weinberg and Bryce DeWitt up here as the representatives of it, and also probably not completely fairly. But the argument there is that gravity is better thought of as just an example of an interaction, a gauge interaction, and really everything is a Wilsonian effective field theory, and that's the way we should just think about the problems of gravity, that there's really lots to be learned from other areas of physics. And I want to make a pitch to you that basically both of these positions are wrong. That although I kind of naturally come from the second one, I want to argue that really gravitational systems are more than Wilsonian. So there's a sense in which the exceptionalists are right, that particle physicists, the tyranny of the particle physicist is probably not appropriate. But it's also true that the senses in which gravity is exceptional is not unique. And actually probably the people that are laughing are the condensed matter physicists, because I want to argue that there's a sense in which the issues that arise for quantum systems and gravitational backgrounds are similar to what the issues that arise in other areas of physics. It's just not particle physics. Yeah?
Sorry, I didn't want to assume, but what about holography? That seems like an exceptional thing about gravity.
Yeah, that's true. That is exceptional. Of course, the way that might go is that everything's holographic, and so then it's not just gravity.
Sorry, I missed that, but I'm confused about how that exists in the condensed matter case.
Oh yeah, so I'm not going to aim at that at all. And it might be, in the end of the day, that you're right, that gravity is exceptional and it's because of holography. I'm focusing on something much more mundane than that. So there's an issue that I'm going to get to, which is a problem that arises in areas of physics. And it's the main issue I'm going to talk about is the domain of validity of effective field theory reasoning, essentially, in gravity. And is it sufficient to think in the ways that you do when you're thinking Wilsonian? All right, so I'm not going to argue that the Wilsonian reasoning is wrong. Of course, clearly not wrong. We understand quantum calculation of gravity as a series and a small thing. It's a semi-classical approximation, and there's a small number. And in the Hawking case, it's typically the Planck size or some microscopic size divided by the Schwarzschild radius. In inflation, it might be the Hubble size divided by the Planck scale. And it's not just kind of a qualitative thing. It's not just touchy-feely. There's a formula, and it's formulas like this that kind of quantify the relative size of various interactions in the gravitational effective action that contribute to any particular process. And it's these kinds of formulas that justify the classical approximation in particular, which is what we're typically always using when we're exploring gravity, specifically in cosmological settings for the most part. So I don't want to argue that this is wrong. I want to ask, is it sufficient to have a small energy ratios to justify the semi-classical limit? And the reason I want to ask that is that there's all these things that are puzzles in gravitational physics. There's hints that effective field theory methods are breaking down in surprising places. And those places tend to be at late times, I want to argue. So the two I'm going to focus on that are kind of illustrative of that are, there's issues of secular growth in cosmology. If you take simple cosmological models and you perturb around them, it's often true in a way that I'll make more explicit in a second, that perturbative corrections, the corrections that are proportional to the small coupling constants that you're perturbing in, come with coefficients that are growing with time. And so that kind of secular growth is something which argues that at late times, perturbation theory will be a difficult method to use. There's similar but less kind of cleanly formulated puzzles about late times for black holes. There's all these information loss problems. And all I'm going to use about them really is that there are issues that are always arriving at late times compared to the characteristic time of the black hole, which would be the light crossing time of the black hole. And so the question is that I'm going to build a case, and I'm not going to finish building it, you'll see at the end, but I'm going to build a case towards that there's a generic breakdown. It's not sufficient to have a small coupling constant, and in particular for Wilsonian actions, it's not sufficient to have low energies to justify perturbation theory. Late times is a especially dangerous place. And that's a property that's not unique to gravity. That's something which is generic in other areas of physics, typically not generic in particle physics, because in particle physics we have interactions, we have scattering processes where interactions turn on and turn off because of overlapping wave functions. But that's kind of an exception to particle physics and not generic to physics. So I'm going to argue that, here's what I just told you, that there's a generic issue at late times. It appears in the gravitational situation, and it's similar to what appears in other areas. And I want to remind you why you're not surprised that that late time predictions in perturbation theory are dangerous in other areas of physics. It might not be the way you thought about it traditionally, but if you think about the geometrical optics limit of electromagnetism, the photons, when they're interacting with a medium, are interacting weakly. There's a small chance that any one photon is going to scatter from any one atom. But once you go through billions of atoms, then you hit one. And if you ever get into a regime where every single photon either refracts or reflects and nobody goes straight, you know that perturbation theory is a bad description of that, because perturbation theory says to first approximation, nothing happens. And so that's kind of the illustration that it's really it's a generic situation when you have a medium that perturbation theory fails. But the good thing is it doesn't mean you can say nothing. We know lots about the geometrical optics limit. We know you can calculate the index of refraction, and even though n minus 1 is order 1, it doesn't mean that there was no utility to perturbative methods. And so there are tools that have been developed in these other areas of physics for dealing with this late time situation, and we're crazy not to avail ourselves of them. That's the main message I want to convey. So here's how I'd like to convey it. So you've just heard the motivation, so you don't have to hear that again. I'm going to just remind you of some of the evidence for the secular growth in cosmology, and I'll just kind of telegraphically allude to the understanding that is there of how to resum things at late times. The main thing I'm going to talk about is to what extent do these things happen for black holes, and of course I won't be able to do black holes, so I'm going to start with the simplest case, which will be the Rindler example, and I'll ask how do these issues arise there, and do they arise there, and can they be resummed there? And then if there's time, and there quite likely won't be time, but if not, you'll be motivated to go read about it by then. There's a general approach. So what are these tools that people use? There's a general way to resum late time behavior developed in these other areas of physics, which when you apply them in the cosmology case, actually work very well. And they give you something that cosmologists recognize, stochastic inflation plus corrections. And so that final part will be kind of closing out, if we get to it, the argument that allows you to make progress on late time statements, given that there's a generic problem in making them in perturbation theory. So let's start off with the cosmology part. So what's the story? Why is there what's the evidence for there being a problem at late times in calculating at late times in perturbation theory? So you know that in cosmology, we say a lot of things, but what it comes down to is that there's some scales. In this graph, we've got, we've got length versus time. And so time's across the bottom. And so you've got the Hubble length is the yellow line. It does nothing during inflation, and it takes off. The red line is some typical scale you're trying to follow in the sky. The puzzle is that when you come in at late times and you extrapolate correlations that you see in the sky into the past, they go outside the Hubble regime, and then there's a question of how you explain them. The lovely thing about inflation is that if you track them back far enough, the extrapolation using radiation domination wasn't right, and so eventually they come back inside the horizon. And beyond that, that's lovely in itself, but the picture that there's quantum fluctuations happening as these modes leave, and that's describing what you see as they come back in, is a wonderful picture. And so in that whole story, what's interesting is these super Hubble modes. That's the long wavelength limit that we'd like to understand. And the efficient way to think about that would be in terms of an effective field theory. And I won't get to this in this talk, but there's you might have wondered why people in the 80s, I'm old enough to remember that was the first question people asked, is that you knew that those were the important things. Why deal with models if you can just say some general thing about what the effective action is outside the Hubble scale? Should be simple. Wavelength should redshift away, should be like a quantum mechanics. And of course, no one wrote it down because I think thinking along the lines of Wilsonian actions was the wrong way to think about those things. There is an effective description, but it's just not the one we normally think about. So the big problem is, the big issue is how do you quantify theoretical error when you make a calculation, when you make a quantum calculation or you make a classical calculation. And that's the regime we're interested in thinking about for cosmology. So many of the calculations are based on free fields or close to free fields that are interacting with gravitational background. If you do a calculation of a scalar field and you look at corrections to it, so imagine that you have a scalar field theory, that scalar field, I'm going to think of this not as being the infoton, but as some spectator scalar field. It has self-interactions with a coupling constant lambda. They're generically, the lambdas, these interactions are neglected, and implicit in that assumption is that is the assumption that perturbation theory can be used, and we're thinking of the free theory as being the leading approximation to some perturbative story. And I'm emphasizing that because if there's something undermining the perturbative story, that's going to undermine, it means that it should be undermining your ability to draw inferences from these near-free systems interacting with backgrounds. So if you do calculations of what these interactions do, how they correct things like correlation functions, I haven't done these calculations, but people like Samus and Woodard have done these calculations, and here's an example of it, that if you calculate the 2n, the phi squared to the n correlation function, this is in position space evaluated at the same point, then you get a formula like this. And it's actually, you don't get a formula like this, you actually get something which is an infrared divergent constant which they've subtracted, and then what's left looks like this. And so the thing that I want to draw your attention to is there's a leading term, which is the thing you expected to see involving the Hubble scale, and also involving log of A. A here is the scale factor of the FRW background, which during inflation or in a de Sitter case would be exponential. So those logs of A's are powers of time. And so we knew that phi squared, for instance, was linear in time, and this is kind of the way you see it. But the corrections also come systematically with powers of the logs of A, and that's the secular growth that I was alluding to. That it's, no matter how small lambda is, there's a time for which there's a problem. Now, I tell you this, and of course the first thing you have to say is that there's two obvious objections, or obvious now, but not obvious at the time probably. First objection is that if you're in single field models, all of these issues of infrared physics and late time secular growth are really gauge issues. And so they always drop out of physical things. So one take on these kind of questions is why do you care? And it's true that if your focus is simply single field issues in inflation, you don't really care that much. The story there, these people tell, is that what that scalar field is telling you in these single clock models is essentially how you slice space-time up into time. If you start off with some initial slicing that was very simple, like the blue line, it's just telling you that at late times your slicing is becoming very wildly varying. But if you're calculating gauge invariant things, they don't care about the slicing anyway. You're not so worried about what those slices are and how they grow. But that specific line of reasoning is specific to these single clock models, and it doesn't apply to multiple scalar models. And so it's not really a blanket solution to these infrared issues. They really are there, potentially. And so the issues of secular growth undermining perturbation theory are really, in principle, something that has to be dealt with. The other vanilla comment that you need to make at this point is, what do you hope to learn? It's not like almost certainly what will happen with infrared issues is that they're going to cancel in physical observables. And then typically that happens along the line of the Bloch-Nork-Seat mechanism in quantum electrodynamics. The way I was taught this in quantum field theory class as a graduate student was that quantum field theory is like a Middle Eastern religion. If it rewards you if you're virtuous, but it punishes you, it smites you if you sin. And one way you could sin is to ask a non-physical question, and an infrared divergence is the way that it smites you. And so the famous example of quantum electrodynamics is if you calculate processes with soft photons, like in the left-hand picture, you get an infrared divergence, you connect external lines with photons, and you get logarithmic infrared divergences, and of course they cancel. But the lesson of that cancellation is that there's large logarithms in the answer, that they're not divergent, but they can dominate. And so tracking the infrared effects is often useful, even though you know that they're going to cancel typically. And first of all, you want to see them explicitly canceling in physical observables, but you also often learn something when you see that cancellation happen. So now let's go back to the cosmology. I want to argue in the rest of the story here that what's going on with this kind of secular growth is nothing fancy. It's really, what's basically going on is you have an environment and you're interacting with that environment in a weak way. So you've got some evolution going on, and it'll be some unitary thing like e to the minus I ht, let's say. And the idea is that what's going on is basically the observation that no matter how small your interaction Hamiltonian is, there's always a t for which ht is not small, and you're going to be in trouble. And these calculations are essentially showing you that in various different ways, and what's playing the role of the environment here is the gravitational field. And so it's not like it's remarkable that this is happening in cosmology. We should be thinking of it as being generic, that it happens everywhere in physics. And it does in ways that I'm going to be more explicit. So at this point, so there's a story to tell in cosmology about how you resum that story, which I'll come back to at the end if there's time. But I want to, at this point, follow the thought that these kind of issues are generic and ask, so are they more generic in other gravitational situations? And in particular, to the extent that gravitational systems with horizons are thermal, and thermal things are kind of the poster children for environments, should you expect this kind of secular growth to be generic in other situations where there's where people are interested in quantum effects in gravity, such as black holes and things with horizons which will be thermal? And I'll give a partial answer to that, but it's just really a start to the asking the question. So what you'd like to do is point to a calculation by Woodard and Samus or somebody where you say, oh, here are the secular growth things, and let's now talk about what they mean. And what's harder in the other situations, the non-cosmological situations, is that there's fewer explicit calculations where people actually calculate perturbation corrections around the background. Most of the things that happen with black hole physics are essentially fields that are interacting with the background but not interacting with each other, or the interactions with each other are neglected, or general arguments are often made using properties of Wilsonian actions, which may or may not be appropriate if it's not a Wilsonian action that's relevant. So there's not a lot of examples to point to. So the next tack to take is, well, these things are supposed to be thermal. We understand a lot about thermal systems. Do these issues arise in thermal systems? And if they do, that should be a pointer as to where to look for them in the gravitational situations. So I'm going to run with that a little bit, and I'm going to take the simplest possible case for that, which is almost a paradoxical case, and that is the Rindler example. There's a horizon there. The Minkowski state is supposed to be a thermal state seen by the Rindler observer, and vice versa. And so is it true, but let me focus on that first one, that if the Minkowski state is a thermal state seen by the Rindler observer, do the issues that happen at late time, first of all, I'll convince you that just in a vanilla, not a gravitational, no horizon situation, that there are late time issues in perturbation theory with thermal systems. And so given that that's true, the question becomes, is there a sense in which the Minkowski vacuum, because it's supposed to be thermal, also captures these kind of late time breakdowns? And if that's true, it's almost paradoxical that the zero temperature Minkowski state could have had information about thermal things. So how does that work out? That's something that's flat space. You can do it to death, and so you can understand what's happening in that case and hope to learn something about what's going on in the gravitational case. So what are the funny things? So let's forget about gravity and Rindler to start with and just ask what happens for thermal systems if I have a scalar field. Again, I'm always going to use lambda 5 to the 4th as my example just because it's well studied, it's simple, you can kind of think it through to death. So there's kind of two things that generically happen when you have massless close to massless infrared, light bosonic degrees of freedom, is there's related issues that are happening. This late-time secular evolution is tied a little bit to, I tried to argue that it was completely generic, but there's a sense in which it's not generic. It partly depends also on, it's tied to infrared sensitivity. Because if you have something growing at late times in frequency space, that's something which is singular near zero frequencies. And so the kinds of things that are dangerous are things like massless bosons. And so there are examples, many examples of how infrared singularities are worse for thermal systems than they are for zero temperature systems. And they kind of come in, I'm dividing them into two categories here for purposes of my later argument. And so one of the things that happens, which I'll kind of get to explicitly in a second, is the secular growth story, because that's the story I'm telling. But it's wrapped up with this more broader breakdown of perturbation theory that happens. Breakdown in the language of thermal physics, it's phrased as the breakdown of the mean field methods. When you get close to places where there are light degrees of freedom, light bosonic degrees of freedom. And the basic issue, the reason why thermal fluctuations amplify infrared effects is basically because the Bose-Einstein distribution function is singular for small energies. So if you imagine calculating a graph like this for scalar field theory, where we're looking at a correction to the propagator for the scalar field, and you look at that middle graph, the one that the red arrow is pointing to, and ask, what does that look like? At zero temperature, that would be logarithmically divergent because it has two propagators. So you'd have a d4k, you'd have a 1 over k squared. And so that would be a logarithmic divergence, both ultraviolet and infrared. But at finite temperature, what happens is that you've also got a Bose-Einstein distribution function. And for small k, that's going like 1 over k. So what were logarithmic divergences in the infrared are turning into power law infrared divergences in the infrared. And that happens kind of generically for graphs like this when you have an isolated bubble. It doesn't happen for generic loops, but it happens for a broad class of graphs. And so typically, there's several lessons you draw from that. But one of them is that, that the thing that counts loops in these kind of systems is not what you naively thought it was. It's not the coupling constant lambda divided by 16 pi squared. For some loops, that comes pre-multiplied by factors like temperature divided by the mass if the mass is small, whatever is controlling that ultraviolet divergence. But because it's a power law divergence, it's a power of that mass. And so one way the story then goes is things depend on the mass. The mass itself depends on the temperature. There's this particular graph here corrects the temperature, and famously corrects the temperature, that the temperature at the mass at finite temperature is the zero temperature mass plus a correction which is quadratic in temperature for small mass. And so you might ask, what mass do you mean there? And what you mean there is really the mass, the temperature-dependent mass. And so one way the story gets told is that if you had a massless particle at zero temperature, so m naught was 0, then your mass is not 0 at finite temperature, but it goes like the square root of the coupling constant, square root of lambda. And so when you look at that combination lambda divided by m, that's still proportional to a positive power of lambda. It's not the power you thought it was. So this is the hard thermal loop story, that if you look at massless particles, massless bosons in a thermal bath, the series in lambda that you thought controlled your loop expansion can turn into a series in lambda square root rather than lambda. But it's still summable. So there's a set of tools that you can use to sum that, because the graphs that are giving you this problem are specific classes of graphs that you can track systematically. A more extreme example of that is that if you could, instead of having a massless particle at zero temperatures, you could have dialed the m naught squared to be negative in such a way that the finite temperature mass is 0. That sounds contrived, but that's exactly what you do when you put yourself at a second order phase transition. If you're there, then the honest to God mass is 0, and then basically you're screwed. That perturbation theory really does fail, and that's the right answer. And it's kind of a well-known fact that if you calculate critical exponents near a critical point, mean field theory always does a bad job of describing those, and this is basically the way the theory tells you that that's going to happen. So we know in this situation that there are things that happen due to the fact that finite temperature, the medium is there, it's amplifying things, and we know that in this situation that it's giving us the right answer. Perturbation theory sometimes does fail. It's not sufficient in some cases to have a small coupling constant to believe for perturbation theory. And in particular, I want to focus on late times. What happens at late times? If you take the same graph and you calculate it at late times for late time separations, but at 0 spatial separations, for example, then what it gives you is something like this, something which grows linearly in time and proportional to the coupling constant, with the rest of the dimensions coming from the temperature. So it just illustrates that these secular effects are kind of generic, and when you have these massless boson degrees of freedom at finite temperature. So the goal will be, if that's what happens for thermal systems, can I take a black hole system, or what I'm going to really do is look at the Minkowski vacuum at 0 temperature, but from the point of view of a Rindler observer, and ask, is there a similar kind of story there where the same kinds of graphs and the same kind of a theory are giving me secular growth as functions of Rindler time, let's say. And that seems like that should be, at some level, hard to do because we're talking about, in the end of the day, the flat space Minkowski vacuum. And why should that, if that had a surprise in it, why didn't we know already? And so you'll see that there's the reason, so the rest of this section, I'm going to argue that all these thermal effects are there, and all the numerical factors are such that you get exactly the coefficients that I showed you for the thermal secular growth with the right temperature, if the temperature had been acceleration over 2 pi. But there's going to be an infrared ultraviolet story, which will also tell you why you wouldn't have seen that if you do the calculation the way people normally do the calculation in flat space. And so the rest of this section is meant to be telling you, why, how did that work? So if you evaluate this graph, it's not a big deal. And actually, it's an even easier deal than you think. The loop itself is just a number, essentially. There's no momentum that flows through it. The dependence on the x and y is coming from the external lines. And it gives you something which is proportional to the loop, which is the delta m squared. And there's a logarithm of the invariant separation of the x and y. And the reason it's a logarithm is also pretty clear. These two lines here, if you think of them in momentum space, they would have come to you as integral d4k. If you Fourier transformed everything, it would be d4k with 1 over k squared twice. And then you have an e to the I k dot x minus y. So you got a logarithmically, it's a dimensionless integral basically. And so it's depending logarithmically on the separation for large separations. And so that's kind of what you expect, and that's what you get when you work it out. So it's, and there's some calculable number in front of the logarithm. Delta m squared here is the thing that you would have evaluated the same way you would have calculated. The same story goes through for finite temperature, that the answer is proportional to the delta m squared. And in that case, the delta m squared is the finite temperature mass correction, which is the temperature squared part of it. So if you remember, at late times, the propagator had a secular growth, but there was a t cubed in front of that, the temperature cubed. 2 of those t's came from the mass shift, and then the other t came on dimensional grounds with time. And that's the same thing's happening here, that the mass shift gives you an acceleration squared times lambda, and acceleration over 2 pi is the temperature, the en route temperature, and so this is exactly the same finite temperature. This is exactly the analog of the finite temperature mass shift you would have had if there was non-zero acceleration. Now, if you evaluate this separation along the world line of a Rindler observer, so you're imagining some hyperperbola, and you're parameterizing that by the tau is the Rindler time along that parameter, then the invariant separation as a function of tau is that the third formula, the hyperbolic sign of a times tau, which for large a times tau is an exponential. And so if you put that into the logarithm, you get indeed the thing that I told you were going to get, lambda a cubed times the temperature at that time. And then the coefficient is exactly what you got in the thermal case, is the upshot. And so that's the sense in which the Rindler calculation, the Minkowski vacuum, has a late Rindler time issue. But I lied to you a little bit here, and you could have objected. And that is, when I told you that delta m squared was lambda a squared, you could have said, well, that's actually not what I would have done if I was in the Minkowski vacuum. I wouldn't have. What's really going on there is that this loop is ultraviolet divergent, so there's a counter term there. So you had to choose what you meant by the mass at 0 temperature. And the finite temperature story, the way it works is you say, well, once I've made that choice at 0 temperature, I don't get to remake it at finite temperature. And so if I renormalize the mass to be 0 at 0 temperature, the finite temperature correction is non-zero, and it has to be non-zero, and then I get what I get. In the case of the Rindler calculation, it's less clear what you're supposed to do, because there's really a choice there. There's a renormalization that you have to do, and by doing that renormalization, you're defining what your theory is. So if you're doing what we normally do, you would have said, I choose the counter term to exactly cancel that loop correction, because I do not want my, one way to think about that is that I don't want phi squared to be, the expectation value of phi squared to, I'm defining that in the vacuum to be 0. And so once you make that renormalization choice, then the statement would be that you will not find this answer to be non-zero because it's proportional to delta m squared, and delta m squared is really the sum of that loop plus the counter term, and they're going to give you 0. If you made that choice, then what would it, so a different choice would be if you had been a Rindler observer for whom so let's say that your physical problem was that your field was prepared in a different state, not in the Minkowski vacuum, but you've got an accelerating mirror or something, which is preparing your field in the Rindler ground state. If you thought that was your vacuum and you made your normalization choices such that expectation of phi squared, say, vanished there, then with that choice you would have found this delta m squared that I gave you, and it's with that choice that you find that the Green's function is growing at late Rindler times. The moral of the story is that there's a choice that you get to make because you have a counter term that you have to choose, which is this mass, and you get to choose it once. But then there are two states in your problem. There's the Rindler state and the Minkowski state, and that one choice you made, you cannot remove this late time effect from both of those states. So you can either choose to have it in the Minkowski state, or you can choose, if you were the Minkowski observer and you had calculated the propagator in the Rindler vacuum, you would have found similarly that there was a late time issue. So it's very much like the thermal situation, that there are two states in that case. There's the zero temperature ground state and there's the thermal state. And they can't both, one of them has a late time secular growth. And in that case, it's clear which one you choose because your normalizations are being set at zero temperature. In this case, there's kind of more of an ambiguity, but the statement is that there's no choice for which both the Minkowski and the Rindler propagator, I'm going to say this with too many negatives. It's always true that one of the Minkowski and the Rindler propagator has a late time secular growth. You get to choose which one it is with your renormalization choice, but one of them will always have this late time growth. That's the message. So that's what I just told you. In this case, it's easy to resum things. So what's going on is basically because you've got a non-zero mass shift, all your Feynman rules are the poles of your propagators are at the wrong place. And so the way that the resummation, there's a fancier resummation, but in this case it's a simple resummation. What it really does is it just says you should have been using a massive propagator and perturbing around that. And that changes the asymptotics of your zeroth order propagation. And so in particular, a massless propagator as a function of invariant separation goes like inverse separation squared for large separations. A massive propagator goes like, depends if you're going in the space or time direction, but there's a direction, the one that's going to be relevant in the time direction, it goes like 1 over the invariant separations to the 3/2. So what's happening is that in this case, if you resum this, the secular growth, the answer you get is a massive propagator. The time dependence appropriate to a massive propagator, and it's not that anything's growing. You know, the zeroth order thing, G0 is going like 1 over invariant separation squared, and what's happening is that the resummed answer is going like mass to the 1/2 over s to the 3/2. Everybody's agreeing that for large separations, things are getting small. The reason perturbation theory is breaking down at late times is that if you're perturbing around this, that's a bad choice to perturb at late times because this is not falling as fast as the thing you're perturbing around. And so there's no drama in the stress energy associated with these things. It's just that your starting point is a bad one at late times. And there's a similar story in cosmology, that although things can grow, it's not clear that stress energy grows and that there's a real instability, a gravitational instability tied up with that. There's no evidence for that yet. It may happen, but it's not clear that it happens. So in the Rindler case, going back to the Rindler case, where is late time? Late time, it's late Rindler time, and so it's something which is happening along the light cone. It's something that's not happening at late Minkowski time. It's happening along the light cone. If you tried to predict things that very, 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 as you get closer and closer and closer to that light cone. And of course, that's suggestive for the black hole situation. In the black hole situation, if the same thing happens, and I can come back to what evidence there is that it does happen in the black hole case, which is not conclusive yet, but I'll tell you exactly what the statement is there so far. In the black hole case, the analog of late times for the guy outside would be approaching the horizon, which is the light cone, as you go off to future infinity. And of course, those are where the information puzzles are. So I'm not quite sure how to translate what would be nice would be if somebody could say these information loss count the entropy arguments that people use when they're talking about information loss, if you could turn that into a statement about correlation functions, then you could be very crisp about whether or not there's a problem in the calculation of those correlation functions in this late time regime. But let's suppose that the black hole story tracks what the Rindler story did, which I'm going to argue is plausible, although it hasn't been proven. Then a thing that you might imagine calculating, which would you could hope would have the information about the correlation, the entanglement between the the ingoing and outgoing particle at early times, and then the outgoing particle at much later times, would be a 4-point function where the x's mark the points. So there's 2 points kind of at late times, describing kind of capturing the physics of the pair at late times, 2 x's at the early times, capturing the pair at early times. And if you could translate knowledge of that correlation function into statements about entanglement, I could make this argument precise. But there's lots of reasons to believe that this 4-point function, if it's true that the black hole reproduces what I've told you for Minkowski space, that same problem would percolate into this 4-point function, because any graph you do for this 4-point function always has a line going from the first 2 points to the last 2 points because you want the connected graph. And that involves somebody propagating for a long time along the horizon, which is the dangerous place, essentially. Not all places are dangerous, but that place would be dangerous. What's the evidence that this, should you expect black holes to do this? The honest answer is there's no proof, but the way that if you remember how the argument worked for Minkowski space, in the end of the day, it was a logarithm. What's nice about logarithms is that what you're interested in is the large S limit. The thing that's universal is the small s limit, and for logarithms, the same coefficient controls both of those things. So if that were true for the black hole, and I don't know that it is true, but if it were true for the black hole that the asymptotic behavior is logarithmic in the separation, then you could tie it to the small separation limit in the black hole case, and that's something which you can universally pin down in a curved spacetime. And of course, the behavior in a curved spacetime is always the Minkowski one. It's for small separations, the Hadamard form is the propagator is going like 1 over sigma squared. And so the story, if it's true, another way of saying that is that if the paths that are relevant for this, for calculating these 2-point or 4-point functions is dominated by paths that are near the horizon, then near the horizon it's going to look Rindler, and then the Rindler answer will be a reliable description of what's going on. And if, to the extent that you rely on paths that are making large excursions from the horizon, then it may not be true. And so that's the thing that is not pinned down yet for the black hole. How am I doing for time? Okay, so let me summarize, and then I'll kind of do a telegraphic good news story at the end. So the story so far is that there's various calculations, not that many of them, but it's enough to see that it's not a unique accident in cosmology, where people have done corrections to the zeroth order systems, often for spectator fields, and it's not unusual to find that the corrections come with powers of time. And I've argued that what's really going on there is a combination of the environment is there all the time, you're interacting with it all the time, and so it doesn't go away. So there's a danger of things growing with time. But also, I've refined it a little bit to say that if your things are growing with time, then that meant in frequency space they're singular, and that's the kind of thing that massless bosons or very light bosons can do. So the danger zone is very light bosons in a gravitational field, which are the ones that are often interesting. I kind of tried to extend that story to the horizons, and I did the flat space case because you can do that to death. But clearly you'd want to do that for black holes as well. But here what I want to do is switch gears a little bit to, I've kind of alluded to these tools that are out there in other areas of physics for resumming exactly these issues. And so I want to give a cartoon of the argument as to how those resummations work. And you'll see that when you get to it, there's examples we're familiar with that are special cases of it. And I want to argue also in passing that as applied to cosmology, the nice thing about cosmology in a near de Sitter environment is that there's a lot of symmetry, and so you can do these things more explicitly. That these tools, these general tools, actually are recognizable as things cosmologists used, and in particular, their leading approximation is stochastic inflation, Starobinsky stochastic inflation, but there are corrections to that which play an important role, or can play an important role, depending on what you ask. So the language for this kind of a thing, the difference between Wilsonian physics and this physics, in essence, is that these are open systems in the end of the day. For Wilsonian action, you rely on the fact that you're looking at only some sector of your theory, but you chose that sector because it was separated from the rest of your physics by a conservation law, and that was typically energy. Could also have been energy and baryon number, but you're normally using some conserved thing to separate the things you're not looking at from the things you're looking at. And the great thing about that is that if you start off with the states in your sector, energy less than something, baryon number something, then when you evolve forward in time, you know that conservation laws will keep you in that sector so that you'll have some sort of a unitary evolution. And the only question, there'll be some Hamiltonian that describes that. The only question is, what is that Hamiltonian? And because of that, the description of the effective theories in that context is phrased in terms of actions, because you're really driving at the Hamiltonian. You're not asking, does it exist? In open systems, the first question is, does it exist? So open systems are ones for which that's not true, that you don't have a conservation law helping you. And so you're looking at some subsector A. All your observables are going to be in sector A. You're not looking at sector B, so you're going to try and get rid of that because you're not interested in it. But you don't have anything stopping information from going from A to B or B to A, and so it's more complicated. Things can entangle. There's lots of things that can happen. You can still profit from hierarchies of scale, so there's still a sense in which effective field theories are useful, but they don't come necessarily phrased in terms of an action. And so the Starobinsky stochastic inflation is the example. That is the effective theory of modes outside the Hubble scale, and it comes to you as a Langevin equation or as a Fokker-Planck equation, not as an action, and that's why people didn't find it, except for Starobinsky, for decades. So anyway, so what you'd like to do, if you could solve this, if you know the full density matrix in principle, rho, if you could trace out all the stuff in B to get this reduced density matrix, rho sub A, then you could calculate everything, the time evolution of all your observables, provided all those observables are in A. So that solves your problem. If you know what rho of A is as a function of time. You know how rho itself evolves, and I'm going to use the interaction picture where the states are evolving with the interaction Hamiltonian and the operators with the free part. And then you'd like to know, how do I infer the evolution of rho sub A, given that how rho evolves? And in perturbation theory, it would have been something like this. You have the standard time-dependent perturbation theory story. And it's a mess. What's typically happening, the breakdown of perturbation theory is happening because those time integrals are not necessarily converging. There's lots of things that are complicated there. The first term has the form of a Hamiltonian evolution, but the second one doesn't just necessarily, and that's where entanglement and decoherence and things will happen. The story, in general, it's a mess, but effective field theories don't promise you to solve everything, but they say that there's an efficiency when there's a hierarchy of scales. A useful hierarchy of scale in this context, which is playing the analog of that role, is a separation between the scale of interest to you, which is a long time, because that's the analog of low energies, as opposed to the natural correlation time of the system that you're not looking at. Defined by, if you take the interaction Hamiltonian that connects the two systems, and you do the autocorrelation function, if that falls off to 0 after some characteristic time, that would be your correlation time. It doesn't have to happen, but if it does happen, then if you ask for physics at later times than that, things will simplify, is what the argument is. And in particular, you'd like that correlation time to be shorter than the time over which perturbation theory fails, because you'd like to be able to use perturbation theory to try and learn something about the future. So then the way people make the resummation is they make a coarse-grained time derivative. So what they do is they evolve this density matrix, this reduced density matrix, over some period delta t, and they choose that delta t. So they got a correlation time, which is supposed to be small. There's a time where perturbation theory fails, which is supposed to be big. So there's lots of space in here, and they choose delta t to be something like this. So it's bigger than the correlation time, so they can profit from the fact that correlations are being forgotten. So things will start to look, sometimes they'll look more Markovian. And they won't, what you're hoping is that the evolution, the whole history doesn't matter here, but just where you started from might be sufficient to learn where you ended. But you do it for times small compared to the perturbation breakdown time, with the idea that you can use perturbation theory to evolve things still. And so if you calculate, and if you evolve forward by delta t, you subtract the initial state and you divide by delta t, that's kind of a coarse-grained time derivative. And still you're not necessarily out of the woods, but if it is true that that difference can be expressed in terms of the original variables, like rho sub A, maybe rho sub B. Often this is being done where the system you're not looking at is so big that it doesn't do anything, so you can assume that it just sits there. But that's not always true. The way to think about this would be for the inflationary case. If you can think of things in the slow roll approximation, where things just depend on your initial positions and velocities, or initial positions and not your velocities, then it might be true that you can integrate this system. If you have enough variables on the right-hand side for which you have coarse-grained derivatives, then the logic would be that you integrate those equations. And the important argument is that if you can set this up as a closed system, you can trust the solutions over times that are much larger than delta t or the perturbation time. And that is because, here's the main argument, if you can, all that you need is a series of overlapping regions, delta t, for which that differential equation can be justified, and for which it's true that the right-hand side is a function of the variables whose evolution you have on the left-hand side. If that's true, then the solutions are valid for the union of these overlaps and not for each one separately. And that's why you can believe them for much longer times than the perturbation time. And you've all used this argument. When you say that there's an exponential decay law, even though you calculate the rate for the decay in perturbation theory, and so strictly speaking, the exponential was 1 plus corrections, you really trust the exponential because you've made an argument like this. You knew that dn dt was lambda times n in a whole bunch of overlapping windows like this. And in each of those windows, you could calculate lambda, and it didn't depend on t. And so then the exponential that you got by integrating that, you actually trusted because it was valid over the whole domain, the union of those domains. That's the argument that everybody's using when they resum everything, essentially, as far as I can tell. And it's just in this open EFT language, it's a broader kind of a domain than the standard one. So if you do this for cosmology, now A is the super hub of modes, B is all the shorter wavelength modes in lambda 5 to the 4th theory. Then, and you just follow your nose, then the thing you're trying to calculate is the density matrix for the long wavelength modes, and that has an off-diagonal piece and a diagonal piece. The off-diagonal piece is interesting because that's the decoherence story, and that's something which is actually showing why things decohere quickly. But the diagonal part is the thing that I'm focusing on here. The diagonal part is the probability function, and you can kind of show that it's not generically true that the Schrodinger evolution of a state turns into a Fokker-Planck evolution for the diagonal part of the density matrix. But it is true if you're in a semi-classical limit like the WKB approximation. So when you have modes that are outside the Hubble scale and they're being squeezed because you're becoming very WKB-like, that's what allows you to trade the Schrodinger evolution of the state for the Fokker-Planck evolution, which is this thing here. Fokker-Planck is just that equation up there for the evolution of P. There's a piece coming from the noise, which is called H cubed. That's the modes that are all kind of coming in from short wavelengths to long wavelengths. And there's a piece coming from the derivative of the potential. And the relevance of this to the resummation story is that if you, I think I hid the slide on this, but if you take the Samuelson and Woodard have done the comparison where if you take they had the secular growth, and they ask, if I take those correlation functions phi to the 2n, and I evolve them using this probability, so that's the integral over phi of this probability distribution times phi to the 2n, and I ask, what's the time dependence of that? What they've shown is that this evolution in time, this stochastic evolution coming from this Fokker-Planck equation, captures the infrared part of the full field theory evolution, which is where the secular evolution is coming from. And so, although you can't ask what's happening at late times in the field theory, you can ask what's happening at late times in this part of it, and it's been tested by Samuelson and Woodard that it's capturing the right evolution for short times. And what happens at late times is the Fokker-Planck equation goes to the time-independent solution, which is was with an observation Starobinsky made many, many years ago. And in this particular case, if you had put a general potential up there, it would have been e to the minus v over h to the 4th. You can see that if v is phi to the 4th, that you're evolving towards a very non-Gaussian distribution. I'm just about done, yeah. So the secular growth was telling you something big happened, and this is telling you what it was. You had Gaussian statistics modes coming through the Hubble scale, one after the other, but everyone was very Gaussian. But when you waited long enough, they distorted the distribution function for long wavelength modes to be something very non-Gaussian. But if you take this probability distribution and you calculate the stress energy in those modes, it still goes like h to the 4th. There's not a big stress energy in this evolution. And so the evidence is that there's something big happening, but there's no evidence that I can see that there's something big happening to the stress energy. And so there's what I think Woodard and Samus would like to have happen, and others too, would be that this is a sign, the secular growth is a sign of a breakdown of de Sitter space, and I don't think that it's clear evidence for that. But there is evidence that the secular growth is there, and it's telling you something happened that was big, and there are ways to identify what it is in some situations. So bottom line, what did I tell you? Tell them what you're going to tell them, and then tell them what you told them. So the main message is that was really partly a message against gravitational exceptionalism, but partly also a message against particle physics imperialism, that there's gravity has a lot to learn from other areas of physics, it's just not necessarily particle physics. And so a lot of the intuition that as a particle physicist I come with about late time behavior is coming with trappings that are not generic, that wave packets overlap, they separate, so late times are never a problem then. But they are generically a problem in other areas of physics, as the geometrical optics limit shows you. And so I'm trying to make a case that those issues are the appropriate way that they arise also in the gravitational, for quantum fields in a gravitational background, in particular with horizons, and they should be generic. And so the danger is that the take-home message is that the Wilsonian picture of gravity would have been that it's sufficient to have small curvatures or small derivatives compared to your fundamental scale to trust the semi-classical evolution. And generically, very often that will be sufficient, but there will be specific cases where it's not sufficient. It's necessary but not sufficient. And late times are are one of the generic places where that happens. That small couplings, even though they're small, no matter how small they are, there will be a time for which the evolution calculated perturbatively can break down. But the good news is people have thought about this for a long time because optics has been a subject of study for long times, and there are tools for resumming that late time behavior, and we're crazy if we don't use them. So thank you for your time.